Okay, so let's let's write equations for shear force and bending moment for this problem. What's the first thing that we need to do? More than likely. What's the first step in most of our problems? Let's find our reactions. So I'll assume that I have, I'll call that A, and I'll call this one B. There is a Bx at the pin, but you'll notice there are no x forces, so Bx is going to be 0. We won't worry about that one. So let's come over here first, and we'll sum moments about A, and we'll make sure it's in equilibrium. To make this problem a little easier for us, let's get the concentrated equivalent force of that distributed loading. So the area under the curve is base times height, which is 900 pounds. And it's located halfway. Half the distance is 3.
7 feet.
7 feet?
From A. I mean, from the end.
From the end.
Yeah.
Okay, we're summing moments about A. So about A, let's start here on the left side. This 250-pound force, is that creating positive moment about A or negative moment? Positive. So I have 250 pounds. Its moment arm is 4. Then I have the 900-pound force, positive or negative? Negative. Moment arm of 3 feet. I have By, positive or negative? Positive. Moment arm is 6. And then finally, the 250 on the end creates negative moment. 10 feet. So we should find out that By is 700 pounds. I'm guessing. Bless you. 700 pounds positive. So we assume the right direction. And then we'll go ahead and sum forces in the y direction. So I have AY acting up plus BY up. And then I have all those forces down. So minus 250, minus 250, minus 900. So it looks like AY is also 700 pounds. So far, so good? Okay, so now we're going to write equations for shear force and bending moment. Now, can I write a set of equations that's valid for the whole beam? No. Why? You can see the load is discontinuous. The applied load is easily described here, 0. But then suddenly it changes to some other distributed load and then drops back down to 0. So I'm going to have to write 3 different sets of equations. So the first set of equations I'm going to work on is valid between x from 0 to 4. So I'm going to draw a free body diagram of that little chunk of the beam. That's x long, and it has the 250-pound force there. And then what else? Nothing. So now I'll have positive shear, positive bending moment. Can you solve for those 2 things? Sure. So I'll sum moments at this cut that I made. Make sure they're in equilibrium. So this moment is positive or negative with my right-hand rule? Positive. And then I'll add the moment created by the 250-pound force at a distance of x. So it looks like the moment is equal to minus 250x. And I'll go ahead and put units on there. That'll be kip feet. There's my moment. Now we know from our differential relationships that if I take the derivative of the moment, I should get the shear. So what should my shear be? Negative 250. And that's also easy to check if I sum forces in the y direction. What do I have? Well, I have shear acting down and the 250 pound force acting down. So when I solve for shear, I get 250. So that should be very comforting to you, and that you get these expressions from equilibrium and they also match. Right? We know that the derivative is equal to the shear, and that seems to work.
Is the moment pound per feet or
Kick feet. Oh, it's pounds. You're right. Sorry. Thank you. Okay, so let's draw a line there. And let's do one now that's good from 4 feet to 10 feet. So let's cut the structure somewhere in that region. This one's going to be a little more challenging.
Then we should veto these from the
We should what?
veto. We'll take a vote. Democracy. Come on.
You have to understand that classroom governance is not a democracy. Okay, so then 4 feet away, I have the reaction at A, which I solved for, 700 pounds. And then I have a certain chunk of this. Remember, that was 150 pounds per foot. And we are measuring the distance to that cut as x. So what's this distance right here? That's x minus 4. So what should be my concentrated equivalent force here? F. It's a rectangle. It should be base times height. So that's going to be 150 times x minus 4. And the distance from the cut here, this distance d, what's d going to be? It's going to be half the base, which will be x minus 4 divided by 2. We'll hold on to those for a second. Then I'll go ahead and add to this whole thing that I have positive shear, positive bending moment. Okay? That's probably the most challenging part of this particular problem, was just getting the geometry right. Now you can just plow ahead with your moment. So I'll sum moments at the cut. Let's see what I've got. So I've got my internal moment, which is positive. I've got this force. Is that positive or negative moment about the cut? Positive. So that's 150 x minus 4 times the distance, which is x minus 4 over 2. Then I have 700 pounds. Is that creating positive or negative moment? Negative. So I have 700 pounds times its moment arm of x minus 4. And then I have the 250. Positive or negative moment? Positive. 250 and its moment arm? X. So a little bit of algebra has to be done here. So all this has to be sorted out. Let's see, what am I going to do? I'm just going to take all these terms and throw them to the other side of the equation. So this will all become negative. 150 divided by 2 is 75. And that'll be x minus 4 squared. plus 700 x minus 4 minus 250 x. And you know what? I'm going to leave it like that.
Can you leave it like that on the test?
Why not? It's a valid equation.
It is.
It is.
Cool.
Hopefully it's right.
Yeah. Yeah.
I mean, obviously, if you took your time and multiplied that out, you're going to have an x term from here, an x term from here, an x term from there. You'd have to collect all those something x's. But really,
Ain't nobody got time for that.
right. Ain't nobody got time for that. Now, the only thing this leaves you is when you sum forces to find your shear, is it may be a little more difficult to find this derivative. So summing my forces in the y direction for shear, I've got the shear acting down. I've got my concentrated force acting down. That's minus 150 x minus 4. I've got 700 up. And I've got 250 down. So it looks like the shear is going to be equal to minus 150 x minus 4, and that turns into plus 500. Nope. 450. And of course, if you had time, you could go ahead and simplify that, because there's another negative 600 there to add to the 450. But how could you check that this is working?
See if that's the derivative.
You could take the derivative of this and check the moment. That would take some time to do. What's the other thing you could check? Well, these two things here, moment at 4 here and moment at 4 here, should be the same. Right?
Yes.
And the interesting thing here is that when you evaluate the moment at the first section at x equal 4, that's pretty easy. It's negative 1,000, right? Then I evaluate the moment in the second region at x equal 4. Cool thing is all this disappears, and look, you get the same thing. So that's a quick way to make you feel good about yourself.
But what about the shear?
The shear will not be the same because of this 700-pound force. So when you do the x equal 4 on this side, you see you get minus 250.
Yeah.
When you do x equal here, you're probably going to get the difference, because you're going to have to go from the left side of the 700-pound force to the right side. You get that instantaneous change. Okay, there's one more piece to this, would be the last portion. Let me try it this way. I'll just cover that part up temporarily. So now we'll do between 10 and 14. So I'll make a cut here. I'll look at the right-hand side. So this will be a pretty simple little free body to do. All I'll have is the applied 250-pound force, and that will be at some distance x away. So what's the little length of the section? 14 minus x, because the total length is 14. And then at that cut, I have positive shear and positive bending moment. So summing the moments about the cut and setting them equal to 0, this moment will be negative. The 250-pound force is also creating negative moment with a moment arm of 14 minus x. So the moment is equal to negative 250 times 14 minus x. So what's the moment at the free end? 0. Does it work? X equal 14? 0. That feels pretty good. And probably that's going to be a lot easier equation to quickly take the derivative of to check our shear. Our shear force is acting up. The 250 is acting down. So it looks like shear is equal to 250. And if you take the derivatives with respect to x, you get 250. Mr. Simpson.
Okay, so I just want to make sure you only cut the beam once per diamond, per section.